As mechanical engineers, we don't use AI or AI tools very often. For me, it is mainly because I don't trust these tools. However, I thought it would be a nice experiment to let ChatGPT assist me in designing a quadcopter FPV drone to 3D print at home. I wanted to see where the generic version of this GPT assistant will go wrong. First things first, let's see what is out there. As a disclaimer, this is my first time designing something like this, and looking at Google, I can get the hang of what it looks like and get a general idea of the design. Now let's jump to ChatGPT and start asking some questions. So, that's a nice start. It immediately feeds me with basic information. Props. Motors. Motor-to-motor distance. What to expect for the weight of it. I like that it is not professional, and it eases it in with general information. Okay. I guess I should aim for 22/7 motor. Or a motor like it. Good to know we need to consider motor thrust and crash loads. Selecting a layout, I think X is what we'll go for. Stack area. Need to take this information when laying out the electronics. Since it will be 3D printed, it is important to have a proper thickness. From my experience, at this point of time I think these numbers are okay to use. But we will check it later. Now, it seems like we need a flight controller, VTX, RX, camera, and a battery for our electronics. CG. This is very important for the drone's stability and to the flight controller alignment. So far, no strikes for GPT. And now to the more interesting part of this project. If we assume a total weight of this drone will be 1.5 kilograms, then I think it is safe to take 1 kilogram of force for each arm. For the design goals, a safety factor of 2 is a good advice. However, this is where I beg the difference on the advice for a crash resistance. I think that 10 to 15 G at 11 milliseconds is something to consider. But we'll deal with it later. Now, here is a good pro tip. I always have a checklist of the requirements to keep track of things. But I usually make it myself. Let's see if we can shortcut here. Cool. Let's organize it a bit. This is very helpful to make sure we did not forget anything. One more pro tip. It is wise to plan ahead what electronics we want to purchase, so we can design accordingly. So maintaining a list of these is also important. And now for the fun part. For CAD design I'm using Fusion 360. This is a free version of it. I've never used it before and thought it would be nice to experiment with this CAD design tool. I've asked GPT to provide a sketch for the design of this drone. GPT gave an X-shaped vector file that wasn't useful. So I guess this is where it ends at this point in time. Design is something anyone can do, but the challenge lies in executing it correctly with a mindset focused on how it needs to function. This is actually where GPT has been helpful so far and can continue to assist in this kind of project. Continuing this design, I began with a basic layout and determined some key components' locations. Now, let's start shopping. I've no idea what flight controller should I buy or what other specific components fit my project. So, back to GPT. One of the benefits is that I set a budget to GPT, and it helped me find components that fit within it. Now I have a complete list of the specific components I need, and also within my budget. To finalize the design, I have arranged the components to ensure that everything fits properly. After several iterations, the initial design is complete. Throughout the process, I frequently revisited the design requirements that were provided to me by GPT. However, before we proceed to production, let's validate our design. I have returned to GPT and asked for instructions. I wanted to see how it would guide me through this process and its recommendations. And yes, absolutely for the fun part. Briefly reviewing GPT's recommendations, I can spot some potential problems. For most of it, GPT is correct for taking 10 to 15 newtons as the normal flight load. However, I think it is not how I would validate the design for a crash load. Crash load or impact is not a simple task to analyze. However, I always advise simplifying a complex problem, so we can use known and simple tools to at least get a better understanding of whether or not our solution is valid. So, as a trick used by mechanical engineers, we define a static load to represent the impact. Although this is an extreme condition, it also helps us understand whether our design needs some modifications to sustain an impact. In real life, this should never replace a formal impact analysis, but for the first draft to understand whether some changes are required to the design, this is a recommended quick and dirty way to do it. Taking the normal loads plus a safety factor of 2, this is how I would start this. Now, GPT recommends 30 to 45 newtons, which are only about 2 to 3 times the normal load. In my estimation, I think 10 to 13 Gs at 11 milliseconds are the numbers to look at. And yes, 10 times the load is a lot. However, we are looking for indications of possible hot spots that can fail in a crash and fix these ahead. Putting it all together, I received about 300 newtons. Now, a still remains question, is it per motor or overall? But we will answer that in a short. Finally, to the FEA software. I use Mechway. I found this free and a very affordable FEA tool that anyone can easily use for these FEAs. This tool can do much more than our simple simulation, and I recommend looking at other tutorials to learn more. Back to GPT. It gave me a clear overview of what I need, plus important information about the material I'm using for the printed parts. This is vital information as 3D printed materials are not well defined yet, and difficult to use in FEA simulations. But overall, I can agree with the recommendations of GPT for how to approach this with the material properties. Bearing in mind that this is an unpredictable 3D printed part, the arm bending case and what to look at are correct, except for the load values, which were manually estimated earlier. Okay, finally. Open new project in Mechway. Import all the assembly STL files. Next, meshing it and review that all looks good and no missing elements. Define the analysis to be 3D static. This drone is constructed out of a few materials, like PETG carbon fiber, PLA, and the standoffs are made of 316 stainless steel. So it is important to set all properties correctly. Also bear in mind that we are validating the design of the PETG carbon fiber part. An impact does not spread evenly across the 4 edges and is hard to predict. However, since I've already accounted for enough safety factors, I will divide the force equally among the 4 motor arms. We only keep that in mind, and we can always evaluate our results and modify the analysis for scenarios closer to reality. Now, let's set the boundary conditions. But for our purposes here, I will stick to what GPT suggested. Fix the center of the chassis and apply loads to the circular surfaces of the motor arms. This will do the job. To the big moment, run! Now we have the results and let's look for these hot spots. But first, why is everything the same color? Since we have different materials, they each sustain stresses differently. To fix this, since we only care about the PETG part, we'll change the color scale of the results to fit with the maximum stresses of the PETG part. And now it's all clear. We can identify the hot spots. Earlier, we set our max stress for the PETG to be around 30 megapascals, so areas that exceed this value would be considered as a hot spots for further analysis and making changes to the design if necessary. Looking for these areas, I found max stress mostly in the sharp corners of the arm connections, and where the standoffs are holding the part. This design was intentionally done this way to test the mechway and for demonstration purposes for FEA. And to fix this, I went back to design and rounded all sharp corners. Running the simulation again, I found a significant improvement in the results. And finally, I can manufacture and fly this toy. Here are some videos of the drone in action. In my flights, I have tested the G-force for hard landing or impact and found it to be 13 Gs for about 10 milliseconds. So I wasn't far off my estimations. As a disclaimer, I hold a UAV license to fly these things. If you plan to try this yourself, this is not an instruction video, and you do so at your own risk. As for the question of whether ChatGPT can help design a drone, then it's definitely a good resource for guidelines, but I'd still take it with a grain of salt. Hope you enjoyed this video. And one last thing, this is not my real voice. This was also done by an AI voiceover,